it simply doesn't matter where you look. All of those problems are in one way or another connected with electromagnetics. And if we were able to really solve these problems and get a community working together on these, we could just make a difference in a whole variety of areas.
Hello, my name is Andrew Geary, and welcome to Seismic Soundoff, in-depth conversations in applied geophysics. I am joined by three guests here to discuss the upcoming 2017 SEG Distinguished Instructor Short Course, or DISC, getting started January 30th in Denver, Colorado on electromagnetics fundamentals and applications. For registration information, visit seg.org/DISC. Dr. Doug Oldenburg is Professor of Geophysics, Director of the Geophysical Inversion Facility, and world leader in geophysical inversions. Throughout 2017 at locations around the world, Doug will cover applications of electromagnetic geophysics across mining, oil and gas, geotechnical, water, and environmental industries. Lindsey Heagy and Seogi Kang, both PhD candidates at the Geophysical Inversion Facility at the University of British Columbia, will join Doug on the upcoming 2017 DISC tour and join Doug and me to discuss the year ahead. Our conversation next. So, Dr. Oldenburg, Doug, you have said that EM geophysics is not well understood and therefore not always applied perfectly. How do you hope to change that with this tour and your work?
The statement that you made is definitely true. EM geophysics is not really well understood. In fact, it's rather complicated in many ways, and that's part of the difficulty. And there's been so many applications of geophysics with different kinds of techniques, and that all makes it a bit more confusing. So I guess our goal is to try to assemble people in a room, a large number of people from various disciplines who all have been interacting with electromagnetic geophysics in a whole variety of problems. We want to get them into a room, and we want to talk to them about different kinds of problems that exist and where electromagnetics can play a role. So that's where we're really going. We're trying to connect real-life problems with fundamentals and see if we can work through case histories and get people to really understand what's going on. And I think with that, and because there'll be so many people from different walks and areas of disciplines, that we can actually make a difference here.
What can participants expect from a day with the three of you? Are you all three going to be at all of these tour stops? Or, with you, Doug, what can participants expect of a day in your DISC class?
With the day in the DISC class, I will be the main presenter, but one of either Seogi or Lindsey will be with me. This is definitely a multi-person event that's required, even for the DISC course. There's actually two parts of this that are happening at each stop. There's a DISC course, which is an 8-hour get-together with people where we talk about case histories and fundamentals, and importantly, try to engage the audience through the use of interactive apps so that they can visualize fields and ask questions about what's going on and be able to get answers. But the second day is going to be something called DISC Lab. This is entirely new, certainly to the SEG, which is hosting this tour. And it consists of an opportunity to get together with a smaller group of people, each of whom has got a particular problem that they're really interested in. We're going to ask them to tell us about their problems. We're going to try to capture that on a sort of a lightning talk and have it posted. And then we want to get together with the whole group, discuss their problems, dissect them, and just see, where there might be new interesting research opportunities, or whether, this was just a dramatic example of a successful use of geophysics. Throughout the DISC lab, if we capture particular problems and have them posted, then you as an academic in another university might look at that and say, wow, that's a really interesting problem. I've never done anything on that. Maybe I should do that. Or from your own perspective, if it's your problem, you've got to a certain part in being able to solve this, and you think, wow, what do I do now? I'm stuck. So if you have a community out there that you can reach out and engage, that can really promote the advancements in the whole field.
So the first tour stop is January 30th in Denver, Colorado. How will those that are going to participate in Denver and at the other locations shape and define this day-long course and the tour as a whole?
The SEG DISC is usually fairly specialized, and it goes around talking primarily to experts in the field. And at each location, there are some exceptions, but I think probably typical attendance is maybe more in the, the 20 to 30 range, right? Which is actually quite effective in the sense that, they're reaching out to the experts, and that may be most of the experts in that particular field at that location. Our mission is a bit different because it's very, very diverse as far as the potential number of people who could participate and benefit. So you actually might be, a geophysicist who knows a lot about many aspects of electromagnetics, but, we might be able to tell you something that, you didn't know about something else. There's also a large number of people out there who are using electromagnetics, the data from there, but really have no real comprehension about what exactly that is, right? There's, in the mining industry that we're familiar with, I can show you all kinds of people that would drill on a first red spot that they saw on a 2D image, right? Without really understanding where that comes from or what's involved. So what I think is going to be our potential impact is, first of all, to have all these people from different areas just getting into a room and realizing, like, oh my gosh, that all these other people are somehow connected with EM geophysics. We're all working with the same 4 Maxwell equations, right? But we're all doing very, very different things. And I think just being in that same room together, the people who are all kind of connecting, trying to communicate, trying to understand what's going on and where this thing can be effective, I think we can make a difference. And that's really the goal of this. We want to increase the use and the usefulness of electromagnetic geophysics.
There's one thing I would like to add to that as well. I mean, one of the big goals that we've sort of set for ourselves and for this tour is really building community. And so having attendees who come actually get plugged into a network of people. And there's so many different ways you can do that with social media and with all these web-based resources. And so I think part of Denver is a bit of an experiment in how do we, gather these people, and how do we make sure that people who are interested can stay connected. And in particular with the DISC Lab, that's an opportunity as well, for people to come and to tell their stories. And so for us, our job there is to also help make sure that story is captured and shared, and make that be a connection point for them as well. So I think that those are some exciting unknowns that we'll be exploring and learning from Denver for sure.
And as you said right at the beginning, the way that we're trying to get connected with individual communities as we're taking the tour is, first of all, contact them, try to get case histories that are relevant to their area. And then we put these on the web. And so now we've got something really tangible when we go. And then on the DISC Lab portion, that's where we'll also capture a lot more information. And, really, if we could get 5 or 8 different case histories at each place that we go to, and we do 30 stops, that's over 200 case histories reflective of all of the problems around the world, and connected, perhaps a lot with, water issues or exploration for minerals or hydrocarbons or geotechnical or geothermal. I mean, there's a lot of commonalities there, and I think that because we're working on the same types of problems and with the same EM types of physics, there are natural connecting points.
Typically a book has accompanied the DISC lecture tour. What have you all built in its place of the book this year?
Yeah, so we have a site called GeoSci, and on that site there's a number of elements. One of them is called EM GeoSci, and this is a resource. It's open source, so it's freely available, and we're actually looking for other people to contribute to this. And it has got a whole host of different aspects with respect to electromagnetics. There's things about the fundamental laws, who developed the initial laws that were eventually put forth by Maxwell. There's ideas about fundamentals of steady state types of process where there's you're just driving a current into the ground and everything is not changing in time. And there's frequency and time domain examples to really understand the physics of what's going on, and then how each of the different surveys works. So there's a whole section on geophysical surveys. So it's a way of kind of connecting everything from the case history to the surveys, to the fundamentals, and for you to allow to actively investigate all of that without being encumbered by actually a big book that it's hard to kind of figure out where you are.
The way we've been developing EM GeoSci, I think, is quite exciting. Is we've had like 17 contributors who've been able to jump in and add to and enhance the resource. And I don't think that there's many media styles out there that let you do that. I mean, I can't imagine trying to write a textbook with 17 people. Whereas this is actually, we get a bit of structure there, and then we chat about it as a group, and people can jump in and iterate back and forth and have that happen. And also in terms of what we're doing with the apps, a lot of those are actually built on top of open source software that we use for our own research. And so in a lot of ways, it's really exciting seeing these, like the software being used at a whole bunch of different levels. Like it's being used to do cutting edge research. We're wrapping it up to make these interactive visualizations and put slide bars on Maxwell's equations so that you can interrogate, build your own model and see what the currents are doing. But we haven't lost anything along the way. So if you are starting at the starting point and you want to just play with the slide bars and understand how Maxwell's equations are working, actually all of the pieces to go deeper, and if you want to eventually, build up your own simulations and things like that, everything is there. The whole spectrum is there.
We were pushing hard to make it available in online. So you don't need to actually, like what's really bugging us sometimes, actually installing all of these packages and make it work. So we don't want to avoid that. So we want to make online available. So we're using, for instance, like binders and those kind of Python or Jupyter Notebook, those kind of technologies to make it available in online. So it's alive. So people can just go into their website, clicking it, they can start actually these apps. So that's kind of probably important things.
So this is for all three of you. Please finish this sentence. If EM methods reached its full potential, it could...
I guess what motivates me and what has motivated me for my entire career is the ability to use quantitative geophysics to answer important questions. And electromagnetics is connected with so many kinds of problems. I mean, it simply doesn't matter where you look these days, whatever you're doing. I mean, even all the engineering stuff that we have. I mean, we've got lights here, we're communicating, on this computing device. All of that is, Maxwell's equations, right? But on the kind of from that more geophysical side or geoscientific side, there's just so many problems that could be solved or helped solve by using electromagnetics. So long as people know what the potential is, so long as people use it properly, it can really make a difference, whether it's for monitoring issues, whether it's, maybe you're trying to do carbon sequestration and you're, wanting to know where the stuff is going, or all this stuff with fracking, right? Like what's happening underground? Where's it going? How do you find this stuff? Or you're looking for resources, or you're looking for water. Is water table changing? Are we getting contaminants in? Is the permafrost melting? It simply doesn't matter where you look. All of those problems are in one way or another connected with electromagnetics. And if we were able to really solve these problems and get a community working together on these, we could just make a difference in a whole variety of areas.
Picking up on the quantitative interpretation for asking, being able to address important questions, as Doug said, but I think too, integrating with other methods. So with electromagnetics, we're looking at primarily electrical conductivity or resistivity, but to actually fully diagnose any sort of geologic or geotechnical setting or a monitoring problem if we're doing fracking or something like that. It's a piece of the puzzle. And so if we can actually, interface to these other pieces of the puzzle, like seismic, like our geologic knowledge, and actually build up and strengthen those interfaces so that we can get meaningful information into and out of these different fields, I think that would be a game changer in terms of how we are interpreting things in the earth.
So what I personally like is understanding fundamentals. So what I'm excited about, working with Doug with this course is, I want to understand electromagnetics by myself first. And what I want to do, I want to transmit my understanding to the other people. To do that, I need to fully understand. And I don't know, I'm not sure what EM method is reached the full potential. So I think that it's like a steady state where people understand what's going on, what's the fundamentals of EM application fully. So I don't know, I think we could do a lot of things, but I really want to help to get to the steady state that people can understand about this problem. And then they understand this problem, they know how to use this problem for their problem so that we can actually make this helpful to the world.
You've mentioned a few times now this idea of case histories. Could you explain a little bit, to potential participants what you mean by case histories?
Right, so case histories really form a backbone of a lot of what we're going to do. Each case history is divided into 7 steps, which I think most people would think are really natural. The first step is called the setup. So that's where you elaborate on, okay, what is the problem that I'm really trying to solve? What background information do I have? What do I really want to get out? Then the second part is connection with properties. Which physical property? Is it conductivity? Or maybe it's magnetic permeability or dielectric constant? And what ranges should we expect for those things? Once you decide on that physical property, then you can decide, okay, which survey should I take? So I'm going to do an electromagnetic survey, but there's a ton of different surveys out there. So within the context of survey, you need to have some idea about what you're going to get out of a particular type of survey, and how to, where to put the transmitters and the receivers so that you've got good signal. So the next step is then the data. So that's where you actually gone out and acquired the data, just a whole bunch of numbers, time, frequency, tons and tons of numbers, which you can plot up, but they mean absolutely nothing in general, irrespective of how you try to plot them. So that means that you need to do the next step, which is the processing, which might be filtering of the data, making some maps, but generally it's involving inversion. That's where we take the data, we input it into this big mathematical optimization box, and we get out a 3-dimensional model of the Earth, a 3-dimensional distribution of that electrical conductivity. And then the final step is really address the initial question, like, okay, we've got this interpretation. What impact has it had on our on the problem that we set out to do? So that's sort of the synthesis part. So each case history is divided into these 7 steps. And I think by doing that, by compartmentalizing things, it really is easy for people to kind of understand, okay, where are they in the whole procedure? Am I at the data acquisition, or am I having difficulty with the inversion part and the processing, or what? So those case histories then form a lot of purposes, both from understanding where people are, as well as just illustrating what types of problems can be solved this way.
So this is a good way to go into the last question. And again, this is for all 3 of you. How do you see yourself and the field of electromagnetics benefiting from this year-long disc tour?
As in most aspects of life, if you have knowledge and understanding, you are in a position to make an informed decision about something. And I think that's the thing that we can do. We can open up the vision of where electromagnetics can be applied. And we'll do that just simply by showing how many areas that it has been applied. And these are our case history kinds of stuff that we've been talking about. The other is that just fundamental understanding and of what's going on and connectedness. So I think we put all of those things together. We have this ability to get a community that understands what's going on and can responsibly use electromagnetics under the right circumstances, not oversell it. And that's what we want to prevent, right? We want, kind of be a little bit more cautionary, a little bit more, a greater sense of what could be expected on a realistic basis. And I think with that, we'll have really done something that is useful for that community.
In terms of how this year's disc is going, I think it's really interesting in the sense that it is hopefully a starting point for a lot of people. And so in a way, we've been working very hard building EM-Geosci and building up all of these apps to create ways to equip people with knowledge and equip them with ways to interrogate and ask questions. I mean, part of the purpose of creating an app is so that anybody who attends, you now have control over this simulation and you can ask your own questions. You're in the driver's seat. And so this course sort of serving as an introduction and an introduction to EM geophysics as a field, an introduction to some of the resources you can connect with in terms of, finding further knowledge, like what we're trying to do with EM-Geosci, things that you can play with and explore, like these apps. And then eventually getting into, if you're working with data and really do need to be doing computation, getting connected with open source software like SimPeg. And so hopefully this is an interesting starting point to, enable people to actually explore this field on their own a bit further as well.
I want to talk a little bit of open source and open source software development aspect, because we're using a different terminology. For instance, if you're using different languages or different computational languages, sometimes it's very hard to talk to the people, although you're talking about exactly same problem. But what I'm excited about, open source software is the engine of the apps and also a lot of this pieces, but because we're at least working at the same framework in the computational language, and that gives us similar thought process. So when I'm working with the people in a different group or different countries working with the different applications, but I can still talk to them very easily because we're using similar framework and similar numerical tools, which is actually tested and well verified with multiple people. And I think that'll grow, and that'll open up a whole bunch of, that'll actually expand the scope of people, what we can do, what they can do as well. So I think this will motivate this kind of expanding the scope for the other people in the world.
In electromagnetic geophysics, there's a pivotal document published in a book by the SEG, and it was a big chapter by Ward and Homan, which is, I think, used by certainly every graduate student that came through UBC, and I think from a lot of other places too. And that has become, it's kind of like a Bible, right? If you want to know something, you go to Warden-Homan. The thing about that is that if you go to Warden-Homan and you look up an electric dipole in a hole space, you get this equation, right? And it took a lot of work to derive that equation, but there it is. It's an equation. Okay, so what? So when somebody comes along and you program that up and you apply, you compute what the fields are at a particular point, for a couple of different scenarios, or you draw a profile line, right? And then that gets published in a book, right? So that's okay. One picture is worth 1,000 words, right? So we've already got, the importance of the picture. But now you go to an app. It takes that equation and it makes it live, and it connects it up with some slider bars, and you can ask questions, you can visualize fields, you can visualize currents, you can visualize data. I mean, you just get such an insight. And especially by watching things in higher dimensions, you have a better understanding of what your data are like. Your data are always like a particular instrument at a particular place at a particular time, right? So you see something, it's a number. But even if you have a line of data, you can't really figure out what's going on. But if you see the three-dimensional fields, and now you see, oh, I'm measuring this field at this location in this time, I get it. I've got it. I've got this mental image of exactly what's going on. And therein lies the power of this interaction and visualization capability of these apps.
At seg.org/podcast, you will find the show notes and links for all the details for the upcoming Distinguished Instructor Short Course. The first event kicks off January 30th in Denver. Registration info at seg.org/disc. If you enjoy the show, review us on iTunes. Your review helps others find the show. Season 1 of Seismic Soundoff is sponsored by the SEG Wiki, home to hundreds of biographies of key geoscientists, geophysical tutorials, and core content from the science of applied geophysics. Visit wiki.seg.org to learn how you can grow the world's first online geophysics encyclopedia. Original music by Zach Bridges. This episode was produced by Isaac Farley and hosted, edited, and produced by me, Andrew Geary. Thank you for listening. This is Seismic Soundoff, signaling off.